So using Kirchhoff's laws, Kirchhoff's voltage law, Kirchhoff's current law, can be quite complicated once you start having more than the simplest circuit. So I'm going to introduce a new method. It's essentially the same as using Kirchhoff's voltage laws and current laws, but it gives you a prescription for solving a circuit, and I'm going to use it to solve this general circuit. Notice that I have a DC voltage source, a DC current source labeled with their voltages and current, and two resistors. And there are three nodes and two loops. And so I could write down for each one of the branches, I could write down the current that flows through it and solve all the loops and currents and solve it. But the node method gives an easier way of doing that. So in the node method, we start, we label the nodes. So there are three nodes, one of which we pick as the ground node or common. And when we say that that's the ground node, we're saying we're going to compare all the voltages to here. This has a voltage of 0. And so voltage at this node A, we've labeled VA, and this node B, we've labeled VB, are with respect to the 0 being defined here. Okay, and then so through each component, or each, which we call a branch of the circuit, we can label a current. So I'm going to start with R1, and I say that the current goes here from VB to VA. I say for R2, I2 goes like this. For the current source produces a current I3, and there's a current I4 going through the voltage source. Now note, for each one of these I've given an arrow, and at the moment it doesn't matter what direction that arrow is pointing. If when I come to the end of my calculation and get a negative number for I1, that just means that the current is flowing, for instance in this case, right to left rather than left to right. A negative number just is in the opposite of the direction of the arrow. Okay, so I've labeled the nodes, and I've labeled all the currents through all the branches. Now I replace the currents that I can with so at each node then I can apply Kirchhoff's current law and say that all the currents have to add up to 0 coming in, or that all the currents flowing in have to equal all the currents flowing out. Now I'll have one equation for each node, except that I don't need to worry about the ground node because those currents are all accounted for somewhere else. So at VA then I have I1 flowing in, I2 flowing out, I3 flowing in. So I take the ones flowing in, I1 and I3, and they have to equal the current flowing out, I2. Then at node B, I have I4 flowing in and I1 flowing out, so I know that I4 and I1 are equal to each other. So already I see that I've made a simplification. I don't need an I4. Okay, so note that while we calculate voltages at nodes, usually it's the sum of currents at nodes in the node method that we use to solve the system. Okay, now I can replace the currents here with their voltages using the IV characteristic of whatever component. So, for instance, I1 is going to be VB minus VA over R1. And I2 is going to be VA minus 0 over R2. And notice when I write that number down, if I1 is flowing in here, I have to do VB first and VA second. So I replace I1 with VB minus VA over R1. I3, I know what it is directly because I have the current source, so I just replace it with capital I. And the I2 I replace with VA minus 0 over R2. So that's the first equation. I replace this equation for node A with this equation using Ohm's law and the current source IV characteristic. I can do the same thing for node B, except that I don't want to do that in this case because I have a voltage source, and so I know exactly what the voltage difference between VB and V0 and the ground node is. It's exactly B. So VB minus 0 is V. Whenever I have a voltage source using the node method, I'm always going to be able to directly relate the voltage at the 2 points together, and I don't need to use the current at that point. Finally, I have 2 equations and 2 unknowns. I can solve for that. Then first I'm going to plug in VB equals V, capital V. So I plug in a V here. So V minus VA over R1. And then I don't need the 0 there, so I have VA over R2. And that's one equation for V. And notice that I've gotten rid of VB here, so this is one unknown, VA, and I just have to solve for it. I bring VA over R1 over to this side. VA over R1 is here. And I have left V over R1 plus I. And then I just have to divide by 1 plus R1 over 1 plus R2, and I get that VA is capital V times R2 over R1 plus R2 plus I times R1 times R2 over R1 plus R2. And now I've solved the system. I know the voltage here, I know the voltage here, and I know the currents, or I can go back and solve for the currents in each one of these cases. And I've solved the system.